Okay, so measurement approaches. So now we have the instruments, we have the concepts, we have to make the measurements. Somehow you have to come up with a way in which you're going to characterize a piece of ground and match it to what the sensor at the top of the atmosphere says it thinks it's up. And there's lots of ways to do it. You can start to see the lines here a little bit, and I got some better images that are stretched that show it more clearly. The little white dot here is where we would set up our camp. And unfortunately, Yamasan and Obata-san, they probably know this too well at this point. But you would set up camp here, and the reason why we basically chose this area was because you could park here. This isn't the most uniform area, it's not the best area, it's not the driest area. It was the place that we could park a vehicle easily and walk to where we needed to collect data. Measurement of the surface reflected really is as simplistic as it sounds. You have a panel, put the panel down, you lay it out, you level it, take your ASD, look at that panel. You come over here and you will start walking around on your site. And there are a lot of ways, so the subtlety is how you actually walk around. Some groups do it different than others. But
Can I mention something?
Yeah.
I don't think you mentioned it. As you're walking, you're recording.
Well, yeah, I'll get to that.
Okay.
Yeah. No, it's one of the subtleties is there's multiple ways to do it, but the concept is still the same. Site measurement, panel measurement. You know the BRF of the panel because we measured it in the laboratory. And that we know because we had the sample from NIST that had been characterized. So we know the NIST BRF, which gives us the panel BRF, which then allows us to get the site BRF. Now we have to make sure that we somehow make that representative of what the sensor actually sees. So you transport it across the site. In our case, we're collecting spectra at specified intervals. You can set up the ASD to integrate certain lengths of time. The others, some of these, they behave differently, but what's nice is the instrument, because we're doing a ratio, should have no impact on what we're doing. That's why we're doing this ratio approach, is that you should be very instrument independent. As I mentioned yesterday, we think we had a feature in our ASD that created some nice little interesting things. That's the fact that we found that is really kind of a testament to the data collection. So in equations, because it looks much better if you have an equation, even if the equations are just Greek letters and ratios. But basically, step one, you have to get the calibration. So in the laboratory, we're calibrating the panel. So I'm getting digital counts while looking at my panel in the laboratory. And I have the digital counts while looking at the laboratory reference. And I have the reflectance factor of the laboratory reference. That gives me the reflectance factor of the panel. And that is a bidirectional reflectance factor. Technically, it's a biconical reflectance factor because the radiometer has a cone incident, the light has a cone incident. So we're already making an approximation there. So we have bidirectional reflectance with biconical measurements. I take that panel outside and I look at it. So that's step two. Measure the output of the radiometer viewing the field panel in the field. Step three is go out for a walk. Now, as Chris was saying, there's lots of ways. You can basically just collect and keep walking, or you can collect by stopping in one place, and then move and stop and collect. So there's multiple ways to do this, and the way the Arizona group did it was we would collect as we walked. And you'll see that was, for me, it dated back to what they did before, and the idea was that it creates a larger sample. It just makes you feel better. It doesn't really create larger sample. You'll see it in a minute. But now you have basically the measurements of the site, the measurements of the panel, and the computation of reflectance factor. Not reflectance, but reflectance factor. It's a bidirectional reflectance factor. But in reality, it's a biconical reflectance factor that we're assuming is a bidirectional reflectance factor. And it's just the ratio of those measurements with the factor of the reflectance factor of the panel. Really simplistic approach. It's It's been the same methodology since Ray Jackson and Phil Slater developed it in the mid-1980s. It hasn't changed at all. And I forget when Nicodemus put out his first papers on reflectance factor, but this has been a concept that's been the same for a long, long time. So in our case, what we would do is we would move the panel with the person. So we'd be walking the site, and we're trying to cover in the push-proof system, we're covering a 300 meter by 80 meter area. And the radiometers can change with time. So to limit the amount of change with the radiometer with time, and sky conditions and other things, basically we would take reference measurements periodically about every 2 minutes. And the easiest way to do that was rather than send a person out 200 back, it was easier to have them just go out 80 meters, come back 80 meters, and they'd walk out along the tiles, and somebody with the panel was walking along this direction, they'd set up and wait for them, and they'd move and they'd set up and wait for them.
Question. This and the other photograph, because when I would look at the sky, it doesn't look that genius. So it's just one. No, seriously, I know if you take care of it.
It's straight light in the camera. No, it never failed, but every time we took a picture, and I just remember this day. And it's really obvious because there was smoke and pollution and things. But the reason I was able to take the pictures is because we were basically not really caring about the data collection. We were doing a repeatability type measurement, and so the students were doing the collection, I had my camera on. But that, thanks for pointing out that.
You're not invited to the party.
You notice here too is, I have nice cirrus clouds in the background there. But again, over the sun it wasn't too bad. We were already there and we were collected, it just made sense. Location of the people, that we talked a bit about this. I don't want to spend a huge amount of time because we're a little bit behind on schedule-wise. But location does play a role, both the people, the optics, the note taker. So this person has not started at this point, and this person is just basically saying, okay, where are you right now? What numbers of spectra do you have? How many transects have you walked? Let's make sure everything is what we think it should be. Collecting of the site of interest, this gets into, again, how we did things was basically continually walking, and that sort of sped things up. It really didn't change things that much, but compared to if you stopped, if you think about it, if I'm always walking, and the instrument's always collecting, that goes just a little bit quicker than if you stop and wait, and then this thing is not collecting now and you move to a new location, you just take a little bit longer. And that causes background sky conditions to change a little bit. The instrument can change over that small amount of time difference. One thing that we took into account was fatigue. So people, they wear out. And so the longer it takes to collect, then the bigger chance you have of somebody making a mistake. All the stability issues come into play. So we try to minimize those effects. And we'll talk a little bit about in terms of uncertainties later on. Gives you an idea of what the sites look like. Here's for Dallas, this is Tsuchida-san down here. So early on, you can see some of the sites, you leave footprints, and that can have an impact on the reflectance. In fact, you can see these lines here, those are basically the tracks where the panel is laid down, and let's see, it shows up better on the next one. Yep, here we go. So here, this is Iconos imagery. This is basically the footprints of the person who is carrying the panel. And that just happens over several years of collections. And here's the pathway that we were walking with the ASD to sample the 15, 20-meter pixel sizes that we were trying to do. Turbulence marking the corners. What you see going this way is we can do Landsat. In the original Landsat systems, 4, 5, and 7 were whisk broom scanners. So they were scanning basically across the page. And the size of that site is 16 Landsat detectors. So it's 480 meters long, and it's 4 detectors this way. So this, you get the 4 samples to try and get an idea of what's happening to that detector as you scan. And the 16 that way, the idea is you're sampling all the detectors on the system. That dates back to 1984. The very first time that they ever did Landsat 4 out at White Sands Missile Range, somebody decided that, well, we want to do all of the detectors. Okay, that makes sense. And we don't want to do just one sample of all the detectors. We'll make sure we get a few samples so we can average. So let's do 4. That gives us a factor of 2 improvement if they're noisy. Okay, so we'll do 16 by 4. Everything is propagated from that. This used to be 16 by 4 in terms of the push boom systems, the French, but the French footprint size was 20 meters, and they didn't want to do 320 meters. So it became 300 meters wide, it was 15 pixels. There's no statistical reason for doing this, and we know that. This is just a bunch of people guessing back when they first started working, and nothing changed since then. So I ended up leaving Arizona about the time that we had decided that we were going to completely shift how we were doing the sampling and get more metrologic-like as opposed to just being remote sensors that kind of, well, it's the first time we're doing something, let's just set it up. I like to pick on JPL periodically. In the United States, I'm at NASA Goddard, and there's another NASA facility that's JPL run opposite sides of the country, and we are a little competitive. This is what happens when you let somebody at JPL use your test site. I work with the Japanese, I work with the Malaysians, I work with multiple countries, multiple other organizations. They all walk the same path. And then the one NASA group, we'll just walk right back across. That makes no difference, really. It's a high stretch there. And as you start to see, the numbers are really quite frightening. Do some quick math. Basically, we're dealing with different fields of view, walking continuously. We did that to hopefully increase the size of the area that we're covering. But basically, each data point, though, is 0.06 meters squared if you're collecting at this height. So that's still a little bit optimistic. Most of us were down here. We have 480 samples times 20 samples. So basically, each individual data point is an integration of 20 samples from the spectrometer, and that gets saved as a single file, and we do that 480 times. So you essentially have 580 square meters that you're covering, assuming that each of those 20 are separate, so there's no overlap. The test site that I showed you is 24,000 meters squared. We are sampling 2.4% of the site. And that's doing all of that. The frightening thing is, I'm going to show you later on, I actually only need 4 data points to get within a few percent because of the way the site is statistically. So I could be sampling, instead of 480, I need only 4 times 20. I need only 80 samples instead of that. And so I can basically get rid of a factor of 120 here. I can get down into 0.001% and characterize the reflectance of the site as seen by a sensor in space.
How site specific is that though? You just said this has to, a lot of it is site, layout, all that. So if we went somewhere else.
If we went somewhere else, the same analysis. It turns out where we're going, this would hold true, and in some cases it's still not exactly right because we have a left-right dichotomy. So you want to make sure that you're sampling the quote brighter spot and the darker spots, and so you can't go completely. If you did it completely random, you still should be okay. But there's a site dependency there, and so you still would want to statistically figure out. So once we did the study, the student came back and said, well, why are we walking the site? It's because, well, 1, I can't be there every day, and 2, we're not always in the same place. It might have rained. It's just easier for you guys to do it the same way every time, but we sample it a horribly large amount. But we were going to change the collection because of the fact that you're already at a very, very small level of spatial sampling. It makes no sense to do the way we were doing it by walking continuously. What's interesting, if you actually go through and look at the high resolution imagery, those quick paths is about 2.5% of the site. So if you just measured the footpaths, you could really affect your answer. But what's nice is we would periodically cross paths, and that was enough to get you a sample that was enough to get into the statistics. Takes roughly 30 minutes to collect the site. I take great pride in that. Really, for me, it took about 20 minutes, but it took everyone else in my group about 30 minutes. We've never figured out why that is. They seem to kind of waste time periodically everywhere. You have things, what shows up in this on the screen is there's a few clouds that Martin pointed out in one of the other images. But you have atmospheric conditions that change, sun angle changes, and that depends on season. The smaller the site, you may not be able to get enough data to characterize the site in some cases. If we do it the same way every time, then what's nice is we can cover anything from 0.6 to 50 meters. If you want to do a larger footprint than a 50-meter system, then you need to sample differently. Speeding up would help, but to do that, you might need to collect different numbers of spectra. If you're still trying to sample, what turned out to be the limiting factor was how fast people could walk carrying the equipment. And that's really what led to most of the 30 minutes. The one thing that would help a lot would be reducing the references. And so if you had a really good spectrometer, what you could do is you could leave the panel here, and then you could just walk out and walk back and be done. But the spectrometer isn't good enough for that purpose. And so you really need to be taking measurements periodically, and that slows the system down. So it's the instrument stability that becomes the issue. It does save some time by continuously collecting, but that's not a big deal.
Speaking about the spectral referencing, what do you recommend, or like every 10 minutes or every n second for the spectral panel?
We were doing it it comes out about every 3 minutes, 2 or 3 minutes. And that's about right. And really what it was is ASDs, they need to be optimized periodically because as they heat up, the shortwave infrared detectors really become problematic. And that's every 3 minutes in 35 Celsius conditions is enough to basically allow you to fix that problem.
Did you estimate the change in ambient light during the 30 minutes with those who step out?
No, and I'll bring that up in uncertainties. That's a good question. We have done larger footprints for MODIS, which is a 250, 500 meter, and 1,000 meter footprint size. We directly calibrated a single pixel. We were covering a 1 kilometer by 1 kilometer area and blocked basically this kind of pattern. And that could be done in about 50 minutes. And there we had problems with some of the stability. Our shortwave infrared detector data were not so good because the panel would stay in one spot. And the person would walk, go out, and come back. And it's a very lonely walk. 10, 12 minutes, especially in 35 Celsius temperatures, it's not a pleasant day. But the results were quite good. So then what you do is you take all of the data, you walk this path, and you average it up. And you can take a standard deviation of that average. And standard deviation, depending on the site, can be anywhere from 0.5% to 5%. White Sands Missile Range was the most non-uniform. Lunar Lake Playa was the most uniform of the sites that we used on a regular basis. The rise here is because the reflectance is going down. So really the uncertainty, the variability is the same, it's just the reflectance is lower, which again makes me feel pretty good that what we're seeing is a real non-uniformity. It's a physical thing in the site as opposed to the instrument causing most of it. You have some instrumental features here. This is the detector temperature heating up. I got rid of water vapor bands. You get a little bit of larger noise where you have absorption effects, and that's a signal noise in the instrument itself. Say again? The joint, right here you can kind of see it. That's a good one. Well, I have an example that's way worse than that. You can make it look really bad if you want. And then the other joint is right here in the middle of the water band, so it doesn't really pop out. But what's nice is this site it's a fairly flat reflectance, and it's brown, so it would be nice if it was flat all the way across like Spectralon's, but it's still reasonably good. And that is the average reflectance for this entire rectangle.
Which model
So the question was, is how do we collect with the ASD? And that was a mistake based on, we had somebody who, again, wanted to operate at .005, and they recommended that we did digital number. And that, to stay away from the calibration provided by the instrument manufacturer. If we had operated in radiance mode, we would have found broken fibers much faster. And so if I were to recommend anything, is always operate in radiance mode with the ASDs, because even though you know the calibration is wrong, you're going to divide it out anyways, because you're going to reference to your panel at some point. But that built-in bit of information, you can start to see changes, and what you'll see is you see jumps spectrally, which you will not notice in digital counts, but you will notice in radiance mode. No, radiance. I would use radiance. Reflectance, the difficulty with reflectance is it implies that you started with something that was a reference. And what we want to do is we want to compute the reflectance ourselves. So I would have to take a step of knowing what the reflectance was originally for that first measurement with the ASD to remove that from the data. So your real two choices are digital number or radiance mode. And of those two, I would recommend radiance mode. Retrieving BRDF is a bit trickier. I just have the one chart here. You have to somehow get all the different angles and skip this one.